In this video, we're going to look at transformations of logarithmic functions. So we're going to start by examining the graph of log x base 2, and then plot the graph of log x base 1/2. So we already have the graph plotted for log x base 2, but if we have these x values right here, the question is, what are the outputs, right? So if I input these numbers into the logarithmic function, what will the function output, or what are the y values? So if you input a 0 into this logarithmic function, effectively you're saying log 0 base 2. So what is the exponent on 2 that would produce 0? Well, there is no exponent on 2 that could cause that to become 0. So this value right here does not exist. Now let's look at 1 over 8. Log 1 over 8 base 2. So again, we ask ourselves the question, what exponent on 2 would cause it to become 1 over 8? Well, the answer there is -3. Same thing, we input 1 over 4. What's the exponent on 2 that would cause it to equal 1 over 4? -2. If we have 1/2, what's the exponent on 2 that causes it to be 1/2? -1. And what exponent on 2 would cause it to become 1? Well, if you have 2 to the power of 0, that is 1. So 0. If you insert 2 for x, again, the logarithm returns the exponent. So what's the exponent on 2 that causes it to become 2? Well, that's just 1. What's the exponent on 2 that causes it to become 4? 2, and so on and so forth. So you can see right here how we get our points. See if you can think about the points on the g at x graph, which is log x base 1/2. We can start right away by saying there's going to be no exponent on 1/2 that causes the value to become 0, so this one does not exist right here. And then if you go through this, you should see, like for example, what is the exponent on 1/2 that causes it to become 1 over 8? Well, that's 3, and then fill in the rest. So I'm going to pause the video and fill in the rest of these values. So by inputting the rest of these points here, I can actually now graph this function right here. So just take a look. These are the points, the remainder of the points for these x values. And I can graph this function. So the blue function is your g at x. That's your log x base 1/2. Whereas your red function is just your f at x, which is log x base 2. So the conclusion asks you to compare g at x to f of x. So f of x has a base of 2. G at x has a base of 1/2. So how do these graphs compare? Well, you can see that if you take the reciprocal of the base, the logarithmic graph is a reflection in the x-axis. So the graph of g at x equal to log x base 1/2 is equal to, or is a reflection in the x-axis of the graph f at x is equal to log x base 2. So basically, if we're just trying to show that the relationship between log x base 2 and log x base 1 over 2 is just a reflection in the x-axis. And that'll work for other bases as well. It doesn't have to be 2 and 1/2, right? It could be 3 and 1 over 3, or it could be a and 1 over a. So points on the log function. When performing transformations to the graph, f at x is equal to log x base b, we can use our knowledge of transformations and mapping notation. The following points on a general logarithmic parent function are helpful. And these 4 points plus the equation of the asymptote will be used when graphing a transformation of the parent function. So this is our new parent function that we're learning. This is the logarithmic function. And as you may recall from the first lesson, the logarithmic function is just the inverse of the exponential function. So You input a value of x, and it returns the exponent on b that causes that value of x. So here are the 4 points plus the asymptote on this parent function. Let's take a look at what they would be on a function with base 2. So again, the asymptote wouldn't change. The asymptote there would simply just be x is equal to 0. Then 1 over b, so the base there was b, base here is 2, 1 over 2, negative 1, 1 and 0, that doesn't change, base b, base 2, 2, 1, base squared, so 4 and 2. Okay, so these are your basic points on the parent function of the logarithmic function. And so we use these points to help us perform transformations. So here we go. Here's our first example. Given f of x is equal to log x, and there's no base there, so we assume that the base is 10, that this is the common logarithm. So given f of x is equal to log x base 10, give the equation for y is equal to negative 2 f at 1/2 x minus 1 plus 1, graph the function, and state the domain and range. So the first thing that we're going to look at is give the equation for this transformed function if this is your parent function right here. So I'm going to start right here, and I'm going to say f of x is equal to log x base 10. So as we can see here, I've got a reflection in the x-axis plus a vertical stretch of 2. So I would say, therefore, y is equal to negative 2, right there. And then the function, so logarithm, base 10, I'm not going to write that. I'm going to assume that it's 10 if I don't write anything. And then instead of x, I'm going to write bracket 1/2 x minus 1, and then plus 1, my vertical shift upwards. Now recall that we need to get our horizontal compression factor by itself, so we need to factor it out. So we write y is equal to negative 2 log 1/2 bracket x minus 2 close bracket plus 1. And now we have everything in the format of our transformations. So we have a reflection in the x, vertical stretch by a factor of 2, horizontal stretch by a factor of 2, horizontal shift 2 units to the right, and vertical shift 1 unit up. So I have now given the equation. Now I need to graph the function. So I take my parent function, which is f of x is equal to log of x, and I have my x and y values there. All right, and I think about the base points on this parent function, right? So I think about this right here. Okay, what are the points on that parent function? Okay, well, I start by writing the asymptote, x is equal to 0. Then I look at the next point right here, so 1 over the base, in this case 1 over 10, 1 over 10, negative 1. Then I look at 1 and 0, that stays the same, 1, 0. Then the base, 10 and 1, and as we see here, base squared and 2, 102. Okay, so these are the unmodified points on the parent function of f of x is equal to log x base 10. Now I need to modify them, and I'm going to use my mapping notation. So I can see right here that my k value is 1/2, so that means I have a horizontal stretch by a factor of 2, multiplied by x, and add 2 because I'm shifting right 2 values. Then I have a reflection in the x, so minus 2 y with my vertical stretch of a factor of 2, and then I shift up 1. Okay, so these transformations, this is all stuff that you saw last year in the functions unit in grade 11. And I think we also did a little bit of this at the beginning of this year. So we look at our asymptote. Our asymptote is equal to x is equal to 0. So I can sub that in. 0 times 2 is just 0 plus 2. So my new asymptote is going to be located at x is equal to 2. Then what I'm going to do is I'm going to sub in my x value here. So 2 over 10, okay, plus 2. Well, that would be equal to 2.2. And then negative 1 times negative 2 is positive 2 plus 1, that's 3. So I get 2.23. There's another point, okay? Over here, 1 times 2 is 2 plus 2, that's 4. 1, and I keep going. I keep subbing points in to my mapping notation, and I solve. 22, negative 1, and this is 202, and negative 3. Okay, so I can see that I have to go pretty far along the x-axis. I'm going to go from 0 right here all the way to 200. Okay, that's a lot of ground to cover. So I'm going to make each major x mark here a 10. Okay, so that's 10, that's 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. So it looks like I won't even get to the 200 mark right there. Okay, as we can see, logarithms span quite a large length along the x-axis. Over here though, I can look at my y values, and I only need to go between negative 3 and 3. So I can just go right here, negative 3, negative 2, negative 1, 1, 2, 3, 4, 5, and 6. And then it's just a matter of plotting my points along with my asymptote. Okay, so I'm going to take all these points, plot the asymptote, and come back with the graph. Okay, so I plotted my points, I plotted my asymptote, and now I can just label my graph. This right here is y is equal to negative 2 log 1/2 x minus 2 plus 1. And it actually will continue going down. This was just maybe poor drawing on my part. It doesn't, go back up, but as you can see, it keeps going down further and further and further, right? Until it reaches, 202 and negative 3. So we just kind of sketch it downwards that way. So this is in fact the graph that we plotted right here. And this right here is based off of the parent function, f of x is equal to log x base 10. The next question says the function f of x log x base 10 is vertically stretched by a factor of 3, horizontally compressed by a factor of 1/2, reflected in the y-axis, shifted left 2 units, and up 1 unit. Determine the equation of the transformed function and provide the domain and range without graphing the function. Okay, so basically I'm basing this off of f of x is equal to log x base 10, which I don't write. So if it's vertically stretched by a factor of 3, then what I have to do is I have to write a 3 in front of the function. Okay, that's my vertical stretch. Horizontally compressed by a factor of 1/2. Well, to include that, what I have to do there is I have to remember that I take the reciprocal of k. So that should just be right there, k, or sorry, I apologize, that should be just 2. And we have x. Okay, so that's my horizontal compression. Reflected in the y-axis, so that's got to be negative 2. If it's reflected in the y, the negative is inside the bracket, so I'll have right here negative 2x. That's reflection in y. And then it says shifted left 2 units and up 1 unit. Okay, so I'm going to do my shifts all together. So if it's shifted left 2 units, then I have to write x plus 2 in brackets there. Okay, and if it's shifted up 1 unit, I say plus 1. So what I'll do is I'll write those in red so we can see exactly that That's what I did. So I shifted left 2 units, so that should be +2, and this should be +1, and those are my translations. So recall that we have to go in RST order or SRT order, stretch and reflections first, which I did right here, and then I did my translations last. So here we go. Here's the function, or the equation of the function based off of the description of these transformations. So I've got determine the equation of the transform function and provide the domain and range without graphing. Well, what I do right here is I'm going to provide the domain and range of the original function. And the domain of the original function is x, element of all real numbers, such that x is greater than 0. And the range is y is an element of all real numbers. Okay, no restrictions on the range. Now what I'm going to do is I'm going to think about my transformations here. So I have negative 1 over 2x, and then minus 2. And then my range, or my y values, are 3y plus 1. So I look at my domain here, and x has to be greater than 0. So if I put in a 0 here, okay, so I put in the 0 there, multiply by 1/2, that's still 0. Then I multiply by a negative, so that means that this sign is going to change. So it's going to go this way. And then I subtract 2, so x is less than -2. Okay, so that's my new domain. All I did is I plugged this value in to the x value right there, and I got my new domain. And then my range, well, the range is really not going to be affected by a vertical stretch or by a shift up and down, so I just write y is element of all real numbers. And there we have it. So I started off by coming up with the equation. Then, looking at the domain and range, I looked at the transformations and I put them in this mapping notation format. And then I applied the mapping notation transformations to x is greater than 0. So I subbed in the 0, multiplied by 1/2, still 0, but then multiplied by -1, that changed the direction of the inequality right there. And then -2, 0 minus 2 is -2. And then also noting that y will be unaffected by a vertical stretch in the translation. It's still going to get y as an element of all real numbers. Okay, let's take a look at example 3. What transformations must be formed on this function, y is equal to -6 log x plus 2 plus 1, to achieve the graph of the function y is equal to 2 log x minus 3, again, base 10. So what I'll do right here is I'll start with this equation. Y is equal to -6 log x plus 2, right there, plus 1. And what I'm going to have to do is I'm going to have to think about, okay, well, I'm going to have to, in order to go from -6 to 2, right? So if I want to go from -6 to +2, I'm going to have to reflect in the x-axis, take this graph reflected in the x-axis, so multiply by -1. And then I'm also going to have to divide this by 3. So that means I'm going to have to divide by 3, so that means vertically compress by 1 over 3. So I'm going to multiply by 1 over 3. So let's think about that. Take the -6, multiply by -1, okay, and then multiply by 1/3, that should give you 2. Well, what are those transformations? If you multiply by -1, you're taking this graph and you're reflecting it in the x-axis. And then if you're dividing it by 3, you're vertically compressing it by a factor of 3. Okay, great. So that deals with this right here. That's how I'm going to do the reflections and the vertical compressions to go from -6 to 2. Take a look right here. We have x plus 2. So that means that it's shifted left 2 units, but I want this shifted right 3 units. So what I'm going to have to do to go from +2 to -3, right, to go from, x plus 2 to x minus 3. So recall that's to go from 2 units left to 3 units right. Let's think about that for a second. If my graph is originally 2 units left and I need to go to 3 units right of the origin, then that means I'm going to have to horizontally shift 5 units right. So I'm going to have to add 5 to the x value. Okay, and that will cause it to shift right 5 units. So I'll go from, 2 to the left of the origin to 3 to the right. So I'm shifting it over 5 units. The last thing is we see that this function is shifted up 1, but there is no vertical shift on this one. So this function is shifted up, no vertical shift on this one. So what I'm going to have to do, how am I going to go from +1 to 0? Well, I'm going to have to vertically shift 1 unit down. Okay, so I'm going to have to subtract a unit there. Okay. All right, so effectively, these are all the transformations that I'm going to have to perform on this function in order to get it to go from -6 log x plus 2 plus 1 to 2 log x minus 3. Homework is listed here, plus also this handout right here. Thanks for watching.